The very first trend that we are going to learn is called the atomic radius. Atomic radius, as we talked about before, is basically the size of an atom. Technically, it's from the nucleus to the valence electrons. But you can see that a picture here that it gets larger going from right to left and top to bottom. And so here's like a visual picture of the atomic radiuses on the periodic table in relation to one another. So let's identify the patterns. The atomic radius increases as you go from right to left across a row. Now remember, we don't use row. The vocabulary word you want to use is period. Okay? Atomic radius also increases as you go from top to bottom down a column. Instead of using the word column, we use the vocabulary word group. Okay, so those are the two words you want to use. The question is why, and this goes back to the previous video where we talked about Zeph and energy levels. So let me explain one more time. So here we have a row, so this is going from left to right on the periodic table, from lithium to neon. And so let's write some notes about what kind of information we see here. So lithium has 3 protons, beryllium has 4, boron has 5, carbon has 6, nitrogen has 7, oxygen 8, fluorine 9. All right, we're going to skip the core electrons. Lithium is in the very first column, so it has 1 valence electron. Beryllium has 2, 3, 4, 5, 6, and fluorine has 7 valence electrons. Now, all of these elements are in the second row. Second row means they have 2 energy levels. They all do because they're all on the second row. So let's find out some patterns here. It asks what changes as we go from left to right. As we go from left to right, we have the number of protons change and the number of valence electrons. But let me just say that the number of protons is what's going to be really important as we go from left to right. What remains the same? The number of energy levels. And because the number of energy levels stay the same, it doesn't really become important when we're going right to left. The most important factor between the 3 of these is the number of protons. So remember, protons and Zeph are directly related to each other. The more protons you have, stronger that pull, that hug on that nucleus to the valence electrons, right? So if we look, lithium only has 3 protons, but fluorine has 9. So lithium doesn't have that much attraction, not that many protons, low Zeph, right? So low attraction, but fluorine has 9 protons. That's a lot of protons. That means a stronger Zeph. That hug, that pull is going to be really close together, and therefore the attraction is really strong. Therefore, when you look at the previous picture over here, we see that fluorine is really, really tiny compared to lithium. So here the hug is very, very far away. It's like hugging someone that you barely like. And here you have the hug that is very, very close. All right, So what happens when we go from top to bottom? So here we have lithium, sodium, and potassium. Lithium, sodium, and potassium are going up and down a column. Okay, so if we look here, we are going to notice that there are 3 protons with lithium, 11 for sodium, and 19 for potassium. I'm going to skip the core electrons. Because they're all in the first column, they all have 1 valence electron. Now, lithium is in the second row, sodium's in the third row, and potassium's in the fourth row. So that means lithium has 2 rings, sodium has 3, and potassium has 4, as you can see here. There's 2 there, 3 there, right, and 4 there. So the 2 things that change are, once again, the number of protons and the number of energy levels. And what stays the same is the number of valence electrons. Out of the 3 of these, the most important factor here is the number of energy levels. Those rings are determining how far away our protons are from our electrons. Okay, so let's think about this. The further away it is, larger the distance, right? Out of sight, out of mind, you have less attraction. The closer it is between a proton and electron, then the attraction is really, really strong because it's a really tiny distance between them. Okay, so now that we know this, let's try answering a periodic trends question together. This is what you will see on your practice, your quizzes, and your test. Okay, so here's an example. Which of the following elements has the smallest atomic radius? Arsenic, phosphorus, antimony, or nitrogen? Explain your answer. All right, the first thing you want to do is mark it on your periodic table. This periodic table is extremely tiny, so all you're going to do is make really, really tiny marks. Okay, so here, this is where nitrogen is. Whoops, let me go back. So here, this is where nitrogen is. This is phosphorus. Arsenic, and antimony. Okay, you can use your large periodic table to help you find those elements. If you want to do a quick mark, I usually use a highlighter, but here's a little hard for me to show you with highlighter. Okay, once you notice that they're all in the same column, okay, I'm going to make a note to myself that this is the same column. And remember, column, we use group instead as our vocabulary word. Now it's asking about atomic radius, and we know that atomic radius gets bigger from top to bottom. So I'm going to draw an arrow going down, saying to remind myself that it gets larger as we go down. Now, let's answer the question. It's looking for the smallest atomic radius. The smallest atomic radius then is the one on top. Which element is sitting on top? It's nitrogen. So I'm going to write N for nitrogen. So the questions here are basically filling out parts of a sentence. Now eventually these word choices will go away, but now I am giving you some information here, right? So like these words over here, so you can get a hint as to what goes in the blank. But remember, they eventually go away. So you answer the question, nitrogen has the, and you basically go back to what the original question said. And you're going to write it down. It has the smallest atomic radius of the given elements in this. Period is row, group is column, and we already established that this is a group. The 4 elements are in the same column. So the question is, why does nitrogen have the smallest atomic radius? Well, earlier we talked about when we're going up and down a column, like so, like right here, the most important thing are your energy levels, right? So here we're going to say that nitrogen out of the 4 has the smallest number of energy levels. Right? So if we do a little side note here, nitrogen is in the second row, so it has 2, right? Phosphorus is in the third row, so it has 3, right? And then you have nitrogen, arsenic, which is 4, so it's like 1, 2, 3, 4, right? And then antimony has 5, so 1, 2, 3, 4, 5. That's why we can see here that nitrogen is going to be the smallest atomic radius. It's very small. So it has the smallest number of energy levels. It only has 2. And if that's the case, then we also can say it has the smallest electron distance, right? The nucleus in the middle and the electrons on the outside is very, very small in comparison to its other peers. And because it has a small distance, then remember they're very, very close. So the attraction, because they're very close, they have a larger attraction for one another between that proton and that electron because they are so close together. So, some key things here that we want to go over, okay? So, when you use group as part of your answer, energy levels and electron distance should always go together. If you're talking about a column, columns are all about energy levels, the rings, and distance on how far apart the nucleus and the electrons are. Okay? Another thing that you will always see is that whatever the question is asking up here always goes right here. So you're just copying the same phrase. Another hint that you will see here is that when you write the word smallest here, it's always going to be matching on the next word. Now, the only word that you have to really think about is this last one. This one just depends on what the answer is talking about. So here, you're really going to have to think, is it smaller or larger? It doesn't always match the other two. Okay, but here I color-coded for you that the oranges will always match, the blues will always match, and the greens will always match. So the answer to your problem and here and this word down here are the two you really have to come up on your own. Okay, now that we've done one, let's do one more example together, and then you will do 2 on your own. Okay, it says, which of the following elements has the largest atomic radius? Germanium, cobalt, zinc, or calcium? Okay, first we have to find it on our little tiny periodic table, so use your larger one if you need to. Okay, it wants calcium, right? It also wants cobalt. Cobalt is here. It also wants germanium. And let's see, zinc, which is over here. Okay, went out a little bit of order. All right, so now, first things first, you need to identify what you're looking for, the largest atomic radius. So here you realize that they are in the same row, but the vocabulary word you want to use is period. Okay, so then you think back and you're like, okay, going back to my trend here, I know I'm going to get larger from right to left. So I'm going to draw a reminder arrow to myself that it gets bigger going that way. If I want the largest one, then it's the one that is at the very end here. The largest side is over here, which is dun, 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 calcium. So now let's answer the questions in the sentence. Calcium then has the, so let's sort of color code our way to victory here. The largest atomic radius is part of our question, which then should go exactly here. So largest atomic radius of the given elements in this. And we know that it's a row, so we're going to call this period. Now remember, whatever goes in this box here, the period box, it should match whatever goes here and also what goes here. Okay, so what we know, going back to our notes here, that when we're talking about going across, the most important things are protons and Zeph. Okay, so then let's talk about how we're going to answer this question. So we know that calcium has, let's see how many protons it has. 20 protons. And if we go to the other end here, we know that germanium has 32 protons according to our periodic table. Okay, so you're comparing calcium and germanium. We know calcium has the largest atomic radius, and you got to think why. Because between calcium versus germanium, calcium has the smallest number of what? Of protons. Right? 20 versus 32. And everything else is in the middle. Which means it has something in here. So remember, we know that if it has the smallest number of protons, this word here, it should match this word here. So we'll also have the smallest number of what? Well, we know if we're talking about protons, we're also talking about Zeph. Remember that pull, that hug. Protons are hugging on the electrons. So because it doesn't have that much protons, that hug is very weak. It's a very weak hug. So here you see that period, protons, and Zeph all go in relation to each other. Our green boxes here, smallest to smallest, go together. Now this word right here, I told you, you're going to have to sort of come up on your own and figure it out, right? So let's sort of logically think through this. If we have smallest number of protons, which means it has the smallest Zeph, smallest attraction. Now, if it has the smallest number of protons, which means it has smallest Zeph, which is the pull, then what kind of attraction does that lead to? If you're like, not really going to hug you that strongly. If that's the case, then we know that this results in a smaller attraction, okay, between the electrons and nucleus, which is why it's so big in comparison to germanium. All right, I did these two examples, so look back if you need to and try the next two on your own.